Back in middle school, I used to grind math problems like it was a game of memory. No matter how tricky the concept seemed at first, I could simply practice 100 similar problems before eventually seeing a pattern to it. Man, if I take math in university and keep doing the same thing till I graduate, then I wouldn't have to be stressed for the rest of my student life. My methods were futile against this new foe. Every problem looked so different, and there seemed to be countless ways to solve them. As I practiced proofwriting as its own skill, I began to realize that it has its own set of patterns and rules, though they were definitely less straightforward than the calculation problems I was so used to. So, if you're in the same boat as I was, or if you're simply looking to explore the world of proofs, this video is for you. Like how painting requires a type of paper to paint on, we need to choose a branch of math to practice writing proofs in. Each branch comes with its own set of objects and the definitions associated with them. For a simple introduction to a wide variety of proofs, let's select number theory. Number theory studies integers and their properties. Before we begin writing a proof, we should know what the problem is made up of. First, the statement contains terminology associated with what branch of math we're working in. Let's take a look at the definition. We call an integer even when it is twice some integer. So, multiples of 2 are even. The statement also contains a hypothesis and a conclusion. The hypothesis is our starting point as we write our proof, and the conclusion is our end goal. How do we get from our hypothesis to the conclusion? Let's make them clearer by unwrapping the term using our definitions. Our goal is to find an integer that we can multiply by 2 to get n squared. Since we know that n is twice some integer, we can give it a name, like k. Now, we can't simplify our starting point anymore. Let's see if there's anything relating the hypothesis and the conclusion. It seems like the conclusion refers to n, but it is squared. Maybe we can square this equation to obtain the value of n squared. These two equations look very similar, and we can see that to reach the end goal, we need to show that 4k squared is 2 times some integer. Let's factor out the 2. Since k is an integer, 2k squared must also be an integer. And so, we have found our desired integer. After finishing our outline, we're gonna make it neater and provide justifications for each of our steps. We've just used the method of direct proof to solve this problem, where we went straight from the hypothesis to the conclusion, doing some term unwrapping, manipulation, and wrapping along the way. Let's solve another problem to get a solid grasp of direct proofs. To figure out the hypothesis and the conclusion, we can turn this universal statement into a conditional statement. With our starting point and end goal, we can simplify them by unwrapping the terms. We have a new term here. An odd integer is twice some integer plus 1. After simplification, we can begin thinking how we can reach the goal. Instead of squaring the numbers, we will add them in a way that resembles the conclusion and substitute their values before simplifying. Now, we will change this into the form of 2 times an integer plus 1. Why is this an integer? That's right, it's because s and t were defined as integers. When we want to prove an existential statement instead, our goal would simply be giving an example that satisfies all parts of the statement. Some existence proofs can be solved by finding an obvious example, whereas others require advanced concepts and proof techniques we'll discuss later on. Besides examples, we also have counterexamples. Since the negation of a universal statement is an existential statement, we can find an example to support the existential statement, and hence prove that the universal statement is false. Let's introduce a new concept to reinforce proof by construction. A divides n is equivalent to saying that n is a multiple of a, or n is a times some integer. For example, 2 divides 6 since 6 can be written as 2 times 3, but 2 doesn't divide 5 since 5 is not an integer multiple of 2. This universal statement claims that any 2 integers which divide each other must be equal, and we would like to disprove it. An example may not seem apparent right now, so let's play around with the statement to see any gaps. Since a divides b, a is b times some integer, and same with b divides a. Let's try substituting the first equation into the second one. Dividing both sides by b, we see that nm is 1. What are the integers that multiply to 1? we have 1 and 1, which would mean that a equals to b. But we also have -1 and -1, which means a is equals to -b. So, if we pick two integers that are the negative of each other, like 2 and -2, the hypothesis is true, but the conclusion is false. Hence, we have found our counterexample by poking at the original statement. Besides proving existence, we might also prove the uniqueness of an object. While we know that each integer has an additive inverse, which means that they add up to 0, we may also like to prove that this additive inverse is unique. For example, 2 only has -2 as its inverse, and -3 only has 3 as its inverse. So, our proof has two parts, existence and uniqueness. Let's change this statement into a conditional one so that we have a starting point. First, we'd have to find an example of y to prove its existence. Well, we have -x, since their sum is 0, and -x is also an integer. To prove the uniqueness, let's assume that there are two such values for y that satisfy the additive inverse property, and we'll show that the additive inverse is unique by showing that these two values are actually equal. In other words, we would have to reach this equation using the two equations we have. This is simple enough, since we can combine the two equations. Then, subtract x on both sides to get our desired result, so they are equal. Here's the whole proof. You might have noticed that every integer is either even or odd. We can also group integers into 3 groups based on their remainders when divided by 3. In fact, we can split the integers into any positive number of groups, with remainders going from 0 all the way to 1 less than the number of groups. The remainder can't be greater than or equal to d, since this will wrap back into the other groups. This is a simplified version of the quotient remainder theorem, which says that for any two integers, dividing one by the other gives us a unique quotient and remainder, which can be from 0 to d minus 1. Think of n as the number we put into one of the groups, and d as the number of groups. Then r will decide which group n goes to. For example, 5 goes to the remainder 2 group when there are 3 groups, and 8 goes to the remainder 0 group when there are 4 groups. Our splitting ability helps us in proving statements about integers. Let's rewrite this statement formally. Our goal involves the term even, but whether n is even or odd isn't mentioned in the hypothesis. Lucky for us, we can split the starting point into two cases, one where n is even, and the other when n is odd. If we can show that both cases lead to the end goal, we have shown that the statement is true for any integer. In our first case, n being even gives us our next step, unwrapping the term. Now we have something to substitute n in this expression, and we can manipulate it into the form 2 times some integer. Are you able to do something similar for the second case? Let's try a slightly harder example. We will reformulate this into a formal conditional statement, taking note of the hypothesis and the conclusion. As usual, we'll unpack what the term odd means, and square this to get closer to the goal. These expressions are getting more similar, so maybe we need to manipulate the front. Does this expression look familiar? It is the product of two consecutive integers, which we have proven to be even. With this information, we can write n squared in the form 8 times an integer plus 1. Actually, there is another way to prove this without using the previous result. I'll give you a hint. Odd integers can be divided into 2 groups when divided by 4. In the previous video, we discussed how a conditional statement is equivalent to its contrapositive. We obtain the contrapositive by swapping the hypothesis and conclusion and negating them. This method, proof by contraposition, will be helpful for us when there isn't a clear way to go from the hypothesis to the conclusion in the original statement. For example, this statement isn't very easy if we start from n squared. So, we can swap these statements and negate them. Proving this statement means we proved the original one. Notice that n is an integer that is not even. Since integers are either even or odd, we can simplify the hypothesis and the conclusion. Now this looks very straightforward, and we can apply direct proofs as usual. This is a good time to introduce a new concept, rational numbers. They are numbers that can be written as a fraction of two integers, with the bottom being non-zero. Numbers that are not rational are irrational. For example, a quarter and 2/5 are rational numbers. The sum of two rational numbers is a rational number, and we can show this using a definition of rational numbers and a simple direct proof. Since working with rational numbers is often straightforward, whereas working with irrational numbers are not, we may find proof by contraposition useful when proving statements containing irrational numbers. Turning the statement into a conditional one, we can then find a contrapositive. Now, it is easier to use a direct proof since we can unpack what rational means. We've seen examples of rational numbers, but what about irrational ones? One of the most well-known irrational numbers is the square root of 2. But how do we know that it is irrational? To prove this, we would have to use a new method called proof by contradiction. This works by negating the statement that we want to prove. From here, our goal is to show that this leads to a contradiction, or statement that disagrees with our suppositions. Let's see it in action to get a clearer understanding. Now that we supposed the square root of 2 is rational, we can use the definition of rational and write it as a fraction of two integers. Every fraction has the simplest form, where the top number and the bottom number has no common factors. So let's add an additional supposition that this fraction is in the simplified form. Then, we will manipulate this equation by multiplying both sides by b and squaring them. This equation tells us that a squared is even, and using our previous proof, we can deduce that a is even. Substituting this into our equation, we find that b squared is also even. Again, this means that b itself is even. Now, if both a and b are even, then a over b cannot be in simplified form. This contradicts our claim that a over b is in simplified form. Since this supposition logically leads to this contradiction, it is false, and so our original statement is true. Okay, that was a lot. Let's take a look at a more straightforward example to get used to indirect proofs. Our first step is negating the whole statement before using it to find a contradiction. The negation of a conditional statement is a conjunction of the hypothesis and the negation of the conclusion. Going back to our original statement, we'll put the hypothesis and the negation of the conclusion in a conjunction. This gives us three suppositions, and our goal is to contradict at least one of them. Since n and n plus m are rational, we can write them as a fraction of two integers. Now, we can subtract the second equation from the first, giving us the value of m as a fraction of two integers. This means that m is rational. But wait, our supposition says that m is irrational, so this is a contradiction. This means that the negation is false, and the original statement is true. Let's come back to divisibility. We're now asked to prove that for any positive integer n, 8 raised by n minus 3 raised by n is divisible by 5. It is very difficult to use a direct proof for this, since the only assumption we know is that n is an integer. What about an indirect proof? If we convert this into a conditional statement and take its contrapositive, a direct proof is still difficult since the assumption can't be unpacked. Okay, what about a proof by contradiction? Again, to show that there is a contradiction, we need to do something with this. But unlike when something divides something else, which we can convert into an equation, we can't do anything when something is not divisible. In this desperate moment, we'll try something absurd. What if we prove the statement for each positive integer one by one? When n is 1, this expression becomes 8 minus 3, which is 5, and 5 divides 5. So, the statement is true when n is 1. Doing the same thing, we can prove that the statement is true when n is 2 as well. Okay, you'll quickly realize that it's impossible to keep going, since positive integers go on forever. What if I told you that we only need to prove one value of n? To do this, let's create a machine that detects when a statement is true in one line, and if it is, labels the next line true. This machine does our job for us, since it'll turn all the lines true. The essence of the machine is a conditional statement, and our job is now to simply prove this statement to bring the machine to life. This is where we return to our reliable direct proof, checking the hypothesis and the conclusion. Let's simplify them both. What does it mean for the statement to be true when n is k? It means that 8 raised by k minus 3 raised by k is divisible by 5. Similarly, we can change the conclusion. Suddenly, we have a divisibility statement we can work with as we use the definition to obtain an equation. All we have to do is show that this can be written as 5 times some integer. Let's take the one off the indices. From the previous equation, we can replace 8 raised by k with this. So let's do that and simplify the expression. We'll factorize out the 5, showing that this expression indeed can be written as 5 times some integer. Now, we know that if the statement is true for one number, it is true for the next number as well. Since we proved that it is true for 1, it is true for 2, which means it is true for 3, and so on. Without considering each integer one by one, we have shown that the statement is true for every integer. This video was inspired by chapters 4 and 5 of Susanna App's Discrete Math textbook, where you'll be able to find deeper explanations and tons of problems to practice. I hope that this video served as a simple starting point to writing proofs in math, and that the introduction of the main ideas of each type of proof provides a solid foundation for you to tackle increasingly complex problems. Anyway, I'll see you in the next video.